Thank you.
Okay. Hi, all. Thanks for having us. Thank you, Cozy and Tyler. I'm Tara Pham. I'm co-founder and CEO of Numina.
Hi, everyone. I'm, I'm Pranav Badami. I'm a data systems and backend engineer at Numina.
And so at Numina, our mission is to empower cities with data to become more responsive. We focus a lot on multimodal transportation access, and we do that by measuring, first and foremost, street level activity and translating that into actionable insights for namely planners, but also mobility companies, real estate developers, museums, institutions, kind of anyone who actually has a facilities manager or manages the public realm. And so we're really trying to replace these guys. Traditionally, the interns or the traffic engineers who go out with a clicker and a clipboard and are very expensive conducting impact studies for cities. And because it's slow, it's inaccurate, it's expensive, cities actually don't do it very often. And so we actually largely don't know how many people walk and bike in the street. A lot of our cities are just planned around car counts. So we are a computer vision company. We make a sensor that mounts to light poles and essentially detects and tracks objects in the street. And we, out of the box, measure 5 different modes, but we also measure all kinds of other things. So we detect pedestrians, bicycles, wheelchairs, different types of vehicles, bags of trash, dogs. Kind of if you can see it, we can measure it. And what is unique about our platform is that this is actually just a demo video. We don't save or transmit any video for the data. We process every image on board our sensor. We don't ever collect any personally identifiable information, and we only send what effectively is this tracks data. And Pranav is gonna dive into how that works later. I'm just here to tell you kind of what the end applications and sort of case studies we found are taking this approach to data collection. And so collecting all of this tracks data, we visualize it in a web dashboard. And because we're saving all of the tracks, basically the paths of objects timestamped, we can go back into that data and reanalyze it in lots of different ways through our dashboard and also through various custom reporting that we do. As I mentioned, we do this primarily with our own sensor. We also do take in some other data sources. This is our Gen 2 sensor that we launched in November in downtown Brooklyn. This particular one has a vinyl wrap with our partners on it, but it basically looks like a canister. Usually mounts about 15 feet high. And we're currently live in 12 cities, I think, as of today. We had one just installed this week. And mostly those are in the US. We do work with Sidewalk Labs in their Toronto project, and we also have 2 cities in the Netherlands right now. And so just to kind of give you a sense of how this data looks and the way that we can kind of tell stories, this is a pedestrian plaza actually in one of our Dutch cities called Nijmegen. And green are pedestrians here, red are cars, blue are bicycles. We visualize different objects in different modes in different colors. Obviously, this visualization, usually we would actually show this in a heat map because it's just a sea of pedestrians. This is a train station. Thousands of people walk by every day. And one day we noticed it looked like this. And we thought, oh, that's strange. Something must have happened. We didn't know what. But looking at some sample images we take once per hour, we saw that it snowed. So this is the kind of thing that you can learn from this path data. Obviously, people on the ground knew it snowed, but you can imagine when other events or things you can't explain happen, you can dig back in. And we do collect 1 sample image per hour, and so that's how we have this data. And we save those images for less than 30 days. We automatically scrape any personally identifiable information from that image before any human or software agent sees it on our side. So we're totally privacy first, but we do have some kind of spot check visuals. In another case where we deployed in downtown Brooklyn, we've deployed along Fulton Pedestrian Mall. So it is a street that is intended entirely for pedestrians and city-owned vehicles, so buses and police cars. We measure tons of cars, thousands of cars there every day who are violating the road rules. And what the Downtown Brooklyn Partnership thought was happening is they were coming off of side streets. And just with a very simple behavior zone analysis. So we draw behavior zones in the street. That's some of what Pranav is going to dig into. We were able to actually show that the vast majority of cars are in fact coming from Flatbush, which is the major artery, not side streets. And this is the kind of information that for a planner really helps them think about how to change signage, how to actually do enforcement, how to adjust even time and rules around when cars can access or other vehicles can access the street. Another exciting use case from this site in downtown Brooklyn, we were looking at scaffolding and construction, because actually there's so much development happening in the neighborhood that over the course of our first 6 months, there were multiple construction sites that had actually come up and gone down. And we wanted to see how that affected pedestrian safety. So actually, I'm gonna try to run this slide again. We drew a behavior zone in the street, so that blinking red space kind of tells us when people are crossing in that area. And we found that when this specific scaffolding was erect, that pedestrians actually cross into the street 53.3% more often. And pretty much like clockwork, when the scaffolding wasn't there, obviously in-street pedestrian crossings decreased. This has huge implications for City of New York, because there are almost 300 miles of live scaffolding in the city every single day. And so this is the sort of data that we can get to by understanding, beyond the traditional car counts, actually volumes, paths, speeds, trajectories, dwell times of objects in the street, and by mode. So here we're looking specifically at pedestrians. And so another use case for this, for example, is we were measuring in Jacksonville, Florida. They at the time had the highest pedestrian fatality rate of any major American city. And one of the things that we realized is they were just missing crosswalks where people were crossing. And so we can actually help them before they decide where to locate pedestrian infrastructure, exactly where it should go, to match the desire lines or the natural behaviors of pedestrians. And so there are many of these use cases we've probably yet to discover, but in working in the 12 cities where we work now, and hopefully many more soon, we get to dig into this, and we do some of this sort of analysis sort of out of the box. And then also what's exciting for us as a team is we get to talk to customers and actually kind of dig into these problems as they come. So this is where I'm going to hand it off to Pranav.
I've got this one on already. Yeah, thanks, Tara. So as Tara mentioned, a lot of what we do is enabled by this sort of behavior zone feature that we have as part of our tech stack. So I'm here today to talk you guys through how we do this sort of ad hoc spatial filtering to answer our customers' questions. And let me go through some of those questions, right, just before we dive in. So how many pedestrians crossed the street over the past month? Okay, that's something a planner may want to know. Okay, great. How about this other part of the street? How does that compare? Okay, and then what about during the 2-week period where we close the sidewalk for construction? And what we want to do is we want to have a responsive platform that helps these people sort of answer these questions in an interactive and insightful way. So the rest of this talk is going to be how we build the technology to power that. So as Tara was saying, let's, revisiting some of Numina's principles, we're really about intelligence without surveillance. So we want to provide this sort of data without surveilling people in cities, which means that we do a lot of our object detection, or all of the object detection on the edge, onboard the actual sensors, running computer vision algorithms. And then these sensors transmit, and we store the position and metadata of objects detected in the streetscape. And the reason that we do this is to reduce and eliminate personally identifiable information. So with this sort of like framework of constraints in place, let's dive into it. So here's an example, probably the same sensor that Tara just walked through in downtown Brooklyn. And let's say that we're at a given timestamp, our computer vision algorithms detect a pedestrian in this case. So let's represent that with a little data structure. So we have a sensor ID, a track ID. A track ID identifies a set of detected objects over time as sort of one coherent object. And if the process by which we do that is sort of out of the scope of this conversation, but if you want to know more, Raphael, our computer vision engineer, can talk you through that. And we're also going to be writing a blog post pretty soon about it, so stay tuned. So let's jump forward to the next frame. We collect 2 frames per second. We keep gathering this data. Each time it's a new timestamp and a new set of box coordinates. We keep going, boom, boom. We're taking you through a visual journey here of what our sensor sees. And finally, we detect another object. So this time we detect a car, right? And so now you can see that the sensor ID is the same here, but the track ID is different because we're sort of grouping this set of boxes into a new logical construct. So let's keep going. We keep going, and we're doing multiple object tracking. And sort of at the end, what we're left with is this sort of tale of what happened between timestamp A, timestamp B. And that's really cool. That's great. That's pretty interesting to me right there. But as a customer, that doesn't really get to the question that I wanted to answer, which was how many pedestrians, for example, are crossing at this part of the street, right? Or this part of the street. And we routinely have to answer questions like this for tens of thousands of objects, and we want to try to do it with this sort of responsive dashboard platform and API. And to do that, we have to actually minimize the number of operations that we perform, the number of tracks that we need to process at query time, and eliminate unnecessary work. So the rest of this is going to sort of dig into how exactly we've approached this problem, and then at the end of it, we're going to wrap up with some sort of example cases from our API. And I'll be talking about this sort of stack here, but you can assume that it's sort of layered like this. There's a storage layer, then we query data from that storage layer, and then that queried data is computed upon, and we expose the computed information to our customers in a sort of ad hoc, just-in-time fashion. So let's talk about some pre-processing that we have to do before storage. So these boxes are cool, right? But the customer doesn't really care about the boxes. They care about the paths that the pedestrian actually took through the streetscape. And one good proxy we've found for representing that information is the bottom center of all of these boxes. So that's one thing that we sort of tease out right out of the gate. The other thing, and I'll draw this one behavior zone here as an example to illustrate this, is that the bottom center points in and of themselves are not enough information. You can see here, like, we visually know that the car, the blue boxes in this example, definitely pass through that behavior zone. But if we were simply doing a sort of naive filter on the bottom center points, we would miss that, right? It's not in the same pixel space as that zone. So what we actually have to do is we have to connect these points together, and we use an algorithm called the Bresenham algorithm to do that. It's just takes 2 points as input, and it sort of fills in all the missing pixels in between with a goal of minimizing the error while doing that computation. And then so this is sort of what it looks like when we have the car track and the pedestrian track sort of outfitted with the interpolated points. And so let's remove the image from the discussion now. It's not really super relevant anymore. We can now just focus on these sort of structures as like higher level concepts. So before we had raw sensor data, but now we have these sort of more processed higher level track objects that represent objects' movement throughout the space over a given time. Yeah. Let's remove the points. That's also not really relevant. OK, so let's bring the zones back in, right? So this is the question that we're originally trying to answer. Now, to sort of look at the first step that we take to minimize the amount of work that we have to do, let's consider another hypothetical track that passed through at the same time, right? This track is clearly not intersecting either of the zones that we care about. So ideally, we would be able to discard this track from our computation really quickly. And one way we found to do that is to simply draw boxes around the entire track structure, right? So the min x, the max x, the min y, and the max y that the box traversed throughout its lifespan. And then what we can do at the query layer is we can actually also represent our behavior zones initially as these naive boxes. And we can say, hey, if the boxes of our tracks don't overlap, at least with the boxes of our behavior zones, we know there's no possible way that these things can actually traverse through our zones. So that original track that was orange, we can discard that immediately at the query layer, just using the simple box filter. Now for the remaining tracks, we still need, and now reminder, these boxes did intersect, but we need to make sure that they actually intersected the pixel space that the user created for this behavior zone. So in order to do that, we need to actually check if they intersect. And for that, we're going to use some matrix math. But before we get to the computation part of that, let's dive into that storage layer part of it real quick. And we haven't really talked about that yet, right? But here we can use matrices to our advantage as well. The cool thing about these tracks is they take place over this sort of pixel space that you can think of as our sensor image. And we can really represent them as a set of ones amongst like a sea of zeros, right, that construct the entire image. And so basically, we can reason about them as sparse matrices. And the really nice thing about sparse matrices for us is that it lets us sort of efficiently encode this data, right? So we don't have to store all of it. There are sort of cleaner and more space-efficient ways to do that. So here's a quick example I found online. This is, a 5x5 matrix. So if I was storing all of this data, it'd be 25 values, but there's only 3 non-zero values. But I can actually, by just specifying the row, the column, and the value that occurred at that coordinate, I can represent this data with 9 values instead of 25. And obviously, the scaling of that gets really, really friendly the more sparse your matrix is. And in our case, they're like really sparse. So we're able to sort of leverage that to store a lot of data pretty efficiently. We store it in S3, which is another love-hate relationship, but you can talk to me about that later if you want. But yeah, so we have over 75 million plus tracks stored this way and growing every day. But OK, back to the original thing. So now here I've overlaid this sort of sparse matrix concept on top of the original tracks that we were discussing. And now we can get into the compute layer. And the really nice thing is we can use matrix math here too. We can represent our zones as dense matrices. So sort of now we have like these regions that are packed with ones and then zeros everywhere else. And here I've just extracted a little snippet of code. It's not quite this straightforward in the actual code, but this sort of illustrates the point. So what we can do is really, we can sample the dense zone matrix for all the coordinates in the sparse matrix, basically, where there's non-zero values. And if any of those are non-zero, we know that there's an intersection. And before I move forward, I have heard recently that if you're an aspiring 10x engineer, you don't want to have a white IDE. But this was passed down from design, so spare me. I'm just kidding. OK, so here's an example where the track doesn't intersect, right? And so now when we sample all of those values in the dense matrix, none of them are non-zero, and so we know that it didn't intersect. Before I sort of get out of this matrix space, another really nice thing about the matrix representation is that we can use it to really efficiently compute our heat maps as well. So Tara may have shown you some of the heat maps where you sort of have a different color on the image based on how much activity there was there. And we can compute that output image pretty quickly and with some low-level optimization by sort of representing each of the tracks as matrices. And then here you can see sort of the pixel where those two pads, where the two tracks overlap. That, if we added those two matrices together, would be a 2, right? And then everything else would be 1s. And then compound that over like tens of thousands of rows, and then you get like a nice looking heat map that's sort of more illustrative than just that sea of green that Tara had pointed out before. Okay. Where are we at now? OK, so cool. That's sort of how we do this type of analysis under the hood. But how do our customers actually use this functionality, you may ask? And mostly well, we do have a sort of custom reports that we build out for our customers. A lot of them do interact with this data through our dashboard. And our dashboard is built on top of Numina Graph, which is our GraphQL API. So I'll talk a little bit now about how that's structured, and then also we're sort of at some point in the near future going to release that as a publicly accessible thing for other developers to play around with. So we're going to sort of end with that. So okay, so how do our users, let's start here. How do our users actually create behavior zones? So we have a nice little modal that pops up on our dashboard, and it lets you sort of say, okay, here I'm going to place all these points. I'm going to sort of color this how I want to and give it a descriptive name. And then I'm going to create this behavior zone. And this is basically an example of how you would call a mutation in our GraphQL API. And if some of you guys haven't played around yet with GraphQL, I would really recommend it. It's pretty awesome. But basically, mutations are sort of API calls that you make when you're trying to create, update, or delete any type of data. So here we're creating a behavior zone. So we send a mutation. And we say, hey, like, give it this text, tag it with this sensor that we're looking at, the specific sensor view that the user may be looking at, and here are the coordinates. So I've just put some example ones there, but you get the point. And now here's how that would actually look on the actual dashboard. So now we have a list of behavior zones on the right-hand side, and the user can sort of click on one of them, and then they'll get a nice list of counts, and then they'll also get a heat map visualization for the entire sensor activity over a given period of time. And in this case, it's 7 days. So you can see right above the line graph, there's a thing that says last 7 days and a sort of time interval. And so this is what I was saying earlier. This is why we've sort of gone to some length to do all this work, is because when we didn't have it and we were thinking about just those boxes, this type of computation was really slow, right? It would take a really long time, and we've made significant progress in sort of speeding that up and giving our users a more responsive interaction. So again, real quick, let's take a look at another query. So we also have, so the counterpart to mutations is queries in GraphQL, and our schema is kind of interesting because we actually have analytics built into it. So in this case, we have a query called zone count metrics, which lets you pass in a behavior zone ID, some set of object class types, start time, end time, and a time interval that you want to slice by, and finally like a time zone to sort of anchor the return time values. And here you can see I'm sort of requesting like the following data, like the object class at a given time, and what was the actual count result for that time span. And so this is basically what the output looks like. It comes back in JSON. It says, hey, at this time, there was this 128 pedestrians, yada, 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 and returns as a list. Similarly, we also have a heat maps query. So you can play around with this as well. And we actually have a zone heat maps query, but here I'll just focus on feed. But I realize now that I forgot to update the screen grab there, so sorry. But this should say serial number instead of zone IDs. And then it says object classes again. Everything else. And what you get back actually is a sort of coordinate format encoding of the heat map data. So we get a big long list of an X value, a Y value, and the sort of normalized like activity score at that pixel. So here I just have like 2 examples of that, but this is like a huge list. This is like thousands of like pixel values. And then what our dashboard does is it sort of renders all of that nicely for the user to look at. OK. OK, I see what happened. All right. OK, so where are we going with this? What type of stuff do we want to keep building out for our customers? One thing that we think is really cool is we want to start having composite spatial filters. So right now we just say, oh, like, give me all the pedestrians that pass through zone A and zone B. OK, that's cool and interesting. And it's certainly something that our users couldn't do at this scale before. But what we think is really even cooler than that is to combine those sort of filters into like more interesting logical statements. So get me all the cars that maybe came in, entered zone 3, which is like, let's say, a lane from either this lane or another lane. And that can sort of help us identify better like where traffic is coming and like how to slice and dice it to answer like actual questions from urban planners. The other thing which is really cool is entrance exit analysis. So a lot of customers want to know, hey, like, okay, a pedestrian came through walked into this area, right? But like, where did they come from and where did they leave? How long did they spend there? And what we're sort of working on and doing some research on right now is how can we do that efficiently at scale, and probably we think we found a viable approach using adaptation of this like matrix technique, but we're still working on that and doing some development. So cool. All right, so if you're interested in our API, we are planning a public release for the developer community, the transit techies being chief amongst them. So possible projects that you could work on with this. So number one, we don't really integrate external data sources with this right now. That's definitely something that we would love to have developers working on and exploring, see how users could get value from that. And of course, like there's weather, but there's also GTFS, which, I don't know, Tyler pulled me aside earlier and he was like, you know, it's a legal requirement that you mention GTFS at Transit Techies.
Last slide counts. This is okay.
You could also like explore different types of data visualizations with our API. So yeah, if you're interested in that, find us after the presentations. We're sort of, you know, we have a sign-up sheet. You can sign up to hear more about that. Okay, thanks. And then we're also hiring, which if Tara wants to plug, you can plug.
Immediately, we're recruiting a user research intern. So we think this might be someone who is either transitioning either from the transportation and planning world into maybe UX or market research, or transitioning in the opposite direction, but really anyone who's interested. And then in general, we're always looking for awesome people. This is some of our team now, and we're based in Dumbo, and we work with cities all over the world. So just come find us. Actually, anyone who's a Numina team member, do you want to raise your hand? Yeah, these are the cool all-stars to come chat with. And I think we're going to have a clipboard, so we're really cool. Thanks so much for having us. Thanks, Pranav.
Thank you.
Thanks.